Okay, so for this problem we have block A and spool B, and they weigh 8 and 6 pounds respectively. The spool has a string wrapped around it to which a force P is applied. The coefficient of static friction between the spool and the contact surfaces at A and C are both 0.25. We're supposed to determine the value of P that causes impending motion and determine if slip occurs at A or C or both locations simultaneously. We see that block A is on rollers, so it can move freely up and down also. But what we want to do is really look to see if it's going to slip at A or C first in our example. So let's take a look at this a little bit more closely. See if I can do this right. You can see that this thing could hold at C and slip at A, right? Or we could hold at A and slip at C. It's kind of hard for me to do this, right? And it could kind of roll that way. All right. So let's take a look and see how we can analyze this. Okay, so here are those parts again. If I draw a free body diagram of those, here I have my diagrams themselves, but now we need to add in our forces, right, and look at where slip will be occurring. We do know we do have the weights, right, so for the top block, we have this 8-pound weight of this. We have the weight of this spool going through the centroid. That is 6 pounds. We have this force P applied. Now let's look at our contact surfaces. Okay, so if we look at this, we have a normal force on the bottom of the spool. So always start on the bottom and where we think there's motion, right? And where that motion will be. So if I have this bottom one, this is N1. And if that thing wants to resist motion, right, it's going to want to, this is looking like it wants to go in this direction, right? Well, how do we resist that? We have a force that goes in this direction, F1. Likewise, on the top of the spool, we have a normal force because it's contacting between the two blocks. We'll call that N2. Likewise, there'll be this N2 here. And then if we look at it, again, we can assume that this thing, if it was sliding, maybe wants to go in this direction, right? This is the direction that it wants to slide. If that is the case, then we have to resist that motion, that direction, with a frictional force F2. Remember, though, on our other block, then, it's equal and opposite. So this would be F2 also. And last, we have some reaction forces due to the rollers on the side. This is R sub E, we will call this, and then the other one we'll call R sub D, based off of the values or the parts on the original drawing. So now how do we evaluate this and where do we start? Just like wedges, always start with the topmost object. Usually we have fewer unknowns. It also helps us solve for the normal force between these two objects. So if we start with that, we can sum forces in the y direction first. And if we sum forces in the y, it should be set equal to 0. What do we get? We see that if we sum forces in that y direction, we get that N2 equals 8 pounds, right? This N2 equals 8 pounds. We must again remember our coefficient of friction, mu, for all locations is 0.25. Okay, so this again, it's always good to let us, tell your person looking at your work how you solve it. So this was for block A. This is A. And this is spool B. So the next step then is to analyze spool B, because we don't care about the side reaction forces or anything like that. Let's look at spool B. Okay, and for spool B we have two options for us. We can look and see if slip occurs at C. So this is, again, point C, and this is A up here. Okay, so let's assume slip at C. If that is the case, then that means if slip is at C, down in the bottom, that means F1 equals mu n1. It has to equal mu n1. Okay? And we know that that's equal to 0.25 n1. Well, we don't know what n1 is. We can solve for that too by looking at spool B and then just summing forces in the y direction. So let's do that. So we see when we do that, so for summing forces in the y direction, of course it's the weight of the two objects, so it's 14 pounds. So if we substitute that into our equation here, we find that F1 is equal to 3.5 pounds. And that's only because we have impending slip at C. Okay? If we have impending slip at C, now we can solve for P easily by summing moments at A, right? We don't care about that frictional force up there. We can then solve for P. So let's, on spool B yet, let's sum moments at A and see what we get for P. So if we sum those moments at A, we see that we have P times 9. Where does that 9 come from? It's this radius is 3, and then to the outside is 6. So the moment arm is 9, going in a negative or clockwise direction. F1 is going in a counterclockwise direction, so it is plus 3.5 pounds times 12. The radius is 6. So the distance for that moment arm is 12, and we see when we do that that our P is equal to 4.667 pounds. So again, that was assuming slip at C. Now let's assume slip at A. If slip occurs at A, that means that F2 equals mu n2, we know n2, so that's 0.25, right, times our 8 pounds. F2 is equal to 2 pounds. So this is assuming slip at A, right? So it has to slip at A. So to solve this then, we can look at spool B again, and then we're going to some moments at C, and this will solve for P. So let's take a look at that. So when we do that, what do we get? We have our P again, and it's 3, because now we're only taking moments down there, so the difference between 6 and 3 is 3, so that's that distance. It is wanting to give us a positive moment. And then we see the F2 wants to give us a clockwise direction around point C. That will give us a negative moment, and again, that moment arm is 12. And if we solve for that, we get for P is equal to 8 pounds. So what does this tell us? We compare these two, and we get slip at the lower value of the two. So we are going to get slip will occur at C with P equal to 4.667 pounds.